Welcome to Study Loop.
Let's evaluate the integral. So looking at that denominator, we see a fourth degree polynomial. As usual, if we want to do partial fraction decomposition, we have to check if this factors. So this is a fourth degree polynomial, but it's really a quadratic in disguise. It's a quadratic in x squared. So if you'd like, you can go ahead and define a new variable, w equals x squared. And then we could write the previous equation as w squared plus 5w plus 4. We can factor that. This is just w plus 4, then w plus 1. And then back substitute, and we have x squared plus 4, x squared plus 1. And then we would have to look at these new quadratic factors to see if those can be factored into two linear polynomials. So the way to do that is to recall that for a quadratic of this form, ax squared plus bx plus c, this thing will not factor over the real numbers if b squared minus 4ac is negative. So in our problem, for this first polynomial, we see a is 1, b is 0, c is 4. So b squared minus 4ac is minus 16, which is negative. So that means that x squared plus 4 does not factor. For the other quadratic, a is 1, b is 0, c is 1. So that b squared minus 4ac is minus 4, which is also negative. So that x squared plus 1 also does not factor. So for the partial fraction decomposition, well, we have, first let's go ahead and rewrite the original problem. So the original numerator, 4x plus 3 up there, and then we factor the denominator. So that was x squared plus 4, x squared plus 1. And then using what the author calls case 3 in this section, where we have non-repeated, non-factoring quadratic polynomials in the denominator, we have a linear term up top, ax plus b over x squared plus 4, and then cx plus d over x squared plus 1. So that's our partial fraction decomposition, and the next steps will be to find a, b, c, and d. So taking this new equation over here, let's go ahead and multiply both sides by this denominator on the left. After doing so, on the left, we're just left over with the numerator. But on the right, we have ax plus b, x squared plus 1, and then we have cx plus d, and then x squared plus 4. So let's just go ahead and multiply out and simplify as much as we can. Ax cubed, bx squared, ax, b, and then for the second one, we have cx cubed, dx squared, plus 4cx plus 4d. And then the last thing to write here is to just factor out x cubed. That's a plus c. Factor out x squared. That's b plus d. Factor out x. We have a plus 4c. And then our constant term left over is just b plus 4d. And now we compare coefficients on this latest equation versus the original expression on the left. On the left, we see that the coefficient in front of x cubed is a 1. So that gives us a plus c equal 1. That's one of our equations. And we see that there is no x squared here, or if we like, there's a 0x squared. So that means b plus d must be 0. We see a 4 in front of the x on the left. So on the right, a plus 4c must be 4. And then finally, we have a constant term 3 on the left. So the constant term on the right, b plus 4d, must equal 3. So we have a 4x4 system to solve. Let's go to the next page and write these out and solve it. Our equations, a plus c is 1, b plus d is 0, a plus 4d is 4, and b plus 4d equals 3. So from this first equation, let's say we can solve for a equals 1 minus c. From the second equation, b equals minus d. And then let's see here, from this equation, actually, let's go ahead and plug in this a value over here. So we have 1 minus c plus 4c equals 4. So that becomes 3c equals 3, c equals 1. And then plugging in the c value back over here, we get a equals 1 minus 1 equals 0. And then taking our other equation, b equals negative d, let's plug that in for b on this side. So we have negative d plus 4d equals 3. That means 3d equals 3. So d equals 1. And then plugging this back into this, we get b equals negative d, which is negative 1. So now, let's go ahead and plug in these values for a, b, c, and d into our partial fraction decomposition. When we do so, we'll have negative 1, x squared plus 4. So a was 0, and then b was minus 1, so that's the negative 1 up there. And then we had c was 1, so that's 1x plus d, which is also 1. And then let's go on to the next page to write this out. So let's break this up into 3 integrals. So for the first integral, let me just pull out that minus 1 over x squared plus 4 dx. The second integral, we just have an x up top. And for the last integral, we just have a 1 up top. So let's evaluate these separately. For the third integral, there's 2 ways to go about this, at least 2 ways to go about this. You might remember from differential calculus that the derivative of tan inverse is 1 over x squared plus 1. If you remember that fact, then taking the integral of both sides here, we get that the integral is equal to arctan of x. If you didn't remember that fact, then you can also evaluate this using a trig sub. Here you would take x equals 1 times tan theta, and you would still end up with the same answer, tan inverse x for the integral. All right, so that's the last integral. The second integral, let's do a u sub here. U equals x squared plus 1. This means du over 2 equals x dx. Then we can rewrite the integral as 1/2 integral 1 over u du. That's 1/2 natural log absolute value of u. And that's 1/2 natural log. And then that's x squared plus 1. You don't have to write the absolute value here because x squared plus 1 is bigger than 0. And finally, we have one more integral to go. For this integral, we can go ahead and do the trig sub. Unless you memorize the formula for this, it's very similar to the arctan that happened over here in blue. Otherwise, you could take a trig sub. X equals 2 tan theta. That means dx is 2 secant squared theta, d theta. and then the integral becomes negative. I'm still writing this negative up here. We have negative, and then dx, that's 2 secant squared theta d theta. And on the bottom, we have x squared, so that's a 4 tan squared theta, and then plus 4. Let me go ahead and factor out that 4. So we have a 4 outside now. And then we know, let's pull out the 1/2. We have secant squared and then tan squared plus 1. We know that's secant squared. That's one of your Pythagorean identities. Let's cancel those secant squared terms. You get negative 1/2 integral d theta. That's just negative 1/2 times theta. And then you can solve for theta by taking trig substitution and solving that for theta. So first, divide both sides by 2, and then take arctan on both sides. So that gives us theta equals, we have tan inverse x over 2. So this isn't the final answer, that's just the first integral. We've already solved the other 2 integrals. So the last thing to do will be to just add these answers together. So let's go to the next page to write that up. We have negative 1/2. From the trig sub, we have tan inverse x over 2. Then from the u sub, we have 1/2 natural log x squared plus 1. And then from the other integral, one that we did first, we had tan inverse x. Don't forget the constant c of integration. And this will be our final answer.